Okay, welcome to lecture 23 of Rob 101. We're going to continue on hyperplanes. Instead of 2D discussion that we had, we're going to quickly generalize it to Rn and dimensional vector spaces. And then we're going to look into a problem that basically is a classification problem, supervised machine learning, and how we can formulate our classifier using the simple idea of hyperplane. And that will lead to an optimization problem that we need to be able to solve it. But it has a very famous type. It's called Quadratic Program. And then we're going to look at how we can solve quadratic programs. And we're going to go through some code. We do not intend to do any hand calculations. Okay, so we want to be able to divide the space Rn into two separate parts using a hyperplane. And we want to also learn a notion of distance, the sign distance, to know which points fall into which side. The distance, of course, will tell us how far. But the sign of the distance is also very important for us because it defines the side. And then we're going to see an example of a maximum margin classifier. We talked about hyperplanes as generalization of lines and planes in 3D. So when the dimension is 4 and above, we call it hyperplane. But you should think about lines and planes in 2D and 3D spaces. For example, we have a bunch of hyperplanes, bunch of planes here because these are not in hyperspaces. This is in R3. There, each of them is dividing the space into two halves, but they are also intersecting each other. So what we're going to see, what we want to do, our motivation today specifically is for formulating and solving this problem, although you can come up with many other examples in other disciplines, this is just a good example for basically learning the topic. So I have two class labels, these red circles and blue crosses that you see here. So two categories of data. And there is a model, there's a true model, this black line, that is separating these two categories. Now, our goal is to find a line, in general a hyperplane, like this pink line here in the image, that is as close as possible to that black line, and it can classify the space. In real problem, of course, we don't know the ground truth, that true model that is not available to us. So we are after an approximation of that model to solve this problem for us. I used basically a line here. You can see the line equation, the black line. I simulated this data, so that's my ground truth. But in reality, we don't know the ground truth. So that's where we want to be at the end of this lecture. A really quick recap. So we started looking at lines in a different way. We talked about having a vector A, and that's the normal to the line, then all the points that satisfy this inner product, A transpose X equals 0, this forms a line that is orthogonal to this vector A. And it will go through the origin, because if it's x0, we will get 0. So that defined a line for us, and we could write it as a regressor form. We talked about it. But this had the advantage that we could also define vertical lines using this set. So that forms a line for us. We could write it as a set of all 2D points, such that the inner product or the dot product of A, our vector, A is constant, X can be any point, right? All the points that satisfy this constraint forms the line. And this line passes through the origin, because if you pick x0, it satisfies the constraint. Now, this observation, exactly the way we talked about it, it generalizes to any dimension. So the dot product is general. It works in 3D, 4D, n-dimensional vector spaces. It is exactly the same. The dot product is basically A transpose times X, or sum of product of their respective entries as vectors. So if X is now in Rn, now our constant vector normal to, now we call it hyperplane, should be, of course, in Rn as well. Our hyperplane is defined as all the points in Rn such that the inner product of a constant vector A in Rn and X is 0. This forms a hyperplane. In 3D, that's a plane. In 2D, this is a line. So this hyperplane also passes through the origin, because if you pick X equals 0 in Rn, by now you know that this is a n vector of all zeros. If you plug it into the inner product, it gives you 0, so the hyperplane goes through the origin. So we cannot visualize this. We can only visualize for 2D and 3D. But all the geometric intuition and everything we talked about is valid. And we know that a condition that A, the inner product of A and X is 0, that means that A is orthogonal to all the vectors that lie on this hyperplane. That's how, by definition, that's how the hyperplane is constructed. You can call A a normal vector. Usually it's normalized, but I'll point out, in general, it doesn't have to be, and we take that into account in our distance formula. So we learned that we can divide R2 into 2 halves. And that's basically when the inner product is positive, we get 1/2, which we call it H plus. If it's negative, we get the other half. Why? Now that follows from the angle between 2 vectors. We want to define these half spaces relative to the vector A, right? Not to the coordinates that we usually use. Now, relative to the vector A, any vector that forms an angle that doesn't matter what direction, right, all around this vector, any vector that forms an angle that is less than 90 degrees, right, it falls into one side. If it's more than 90 degrees, it will be the other side. That's somewhat obvious. You can have x1, you can have x2. Now, if you know the angle formula between two vectors, it's the inner product or the dot product divided by their norm. If the angle is 90 degrees, basically the inner product will be positive. And that tells you the angle is 90 degrees, less than 90 degrees. If it's negative, it's the other way. Now, this is also very easy to show. If you have vector A, let's say x, this is vector A, right? I need a bigger vector A, so I can exaggerate. Okay, so the projection of the orthogonal projection of x on A is using the dot product. You've seen it in Gram-Schmidt. That's what we were doing in orthogonalization. So x, it's dot product with A. But we need to divide by norm of A because we want the magnitude of x along A, right? We don't want to scale it just because A is has whatever magnitude. So we divide it by norm of A. Now you know from trig that cosine of this angle, so this quantity is basically this. So the cosine of this angle is x inner product with A divided by norm of A divided by norm of x. So that's the formula for the angle. It's true for 2D, 3D, and dimensional space. And the argument that 1/2 is when the inner product is positive, negative, it follows from this 90 degrees angle. Okay, so this is true. This is true for any dimension, including our Rn in general. And the beauty of it is that it's relative. The half space is relative to the picked vector A, whatever it is.
So in the example that you just had, the thing you drew on the last slide, was that R2, or would that be like?
Well, I'm drawing it, it's R2, right?
Wasn't it three-dimensional though? Like...
Oh, no, the plane is 3D. The angle description was 2D. This is, of course, this is R3, you're right. But this part, I'm talking R2. It doesn't help the argument if it's 3D. It's the same logic, right? It's just you're looking at it in a perspective. And we're just unable to draw if it's R4 and above. But we know it's true. How do we know that? Algebraically, it's true. It's the same operation. We understand dot product, angle. It's just we can't visualize it. So geometry has limitations, but algebra easily can get scaled up using abstraction. So this notion is true, and it carries over to Rn. Now we can divide Rn into 2 halves. The first half is H plus is when the dot product or inner product is positive. The other one is when it's negative. So nothing has changed. It's just our vectors are now longer. They're n vectors. We also learned about affine subspaces. Somewhat confusing name because it's a translated subspace and it doesn't go through the origins. Then it's not a subspace. That's why it's confusing, but it's affine subspace, meaning it's parallel to the original subspace. That is the case when we take our subspace, for example, a hyperplane H, and we translate it with a vector like xc. And by definition, we define it in a way that when we add a vector to a set, we add it to every element of that set. Now, when you translate the hyperplane, for example, this blue line to the red line to the blue line, we talked about it that if you translate this with you have your normal vector, this is xc, right? Pick an arbitrary point, such as x, on the line or hyperplane. Then to get this vector that lies on the hyperplane, we need to talk about x minus xc, right? Otherwise, it doesn't make any sense. It's translated. So pick any vector or point on the plane, then we need to talk about this difference. So the new constraint for the translated version of that hyperplane is that the inner product of A and x minus xc must be 0. This is just generalization of our hyperplane when it does not necessarily go through the origin, because now we can be anywhere. Otherwise, it's too limiting. We have to be limited to all the models, I'll talk about it more, that goes through the origin. That might not be the right model for us, okay? So this allows us to be anywhere in the space. Another name for it is linear variety. That's maybe a better name. So I explained this. The vector x minus xc lie on the hyperplane. That's why this constraint is now equivalent of the original case when it was going through the origin. Now you can look into the constraint. It's basically the A transpose, it's A transpose multiplied by x minus xc, which we get A transpose equals A transpose xc. Now, A and xc are both constant, right? We're given A is a constant vector, xc is just the constant vector. We translated the subspace. Their dot product will be just a number like D, a real number. Now, if A is normalized, then this is the distance from the origin. Now, you might wonder why that's the case. Now, A is the vector that is parallel to the hyperplane. The dot product will project the magnitude of our vector along that direction. What is the strength of our vector along another vector? Namely here, strength of xc, the length of xc along A. That is captured by the dot product of A and xc, which is A transpose xc. On top of that, A is normalized. Normalized means, if it's normalized in this case, that means the norm of it is 1. Then it's just a unit vector, it's a direction. So we basically project our vector to be parallel to the normal of the hyperplane, and then we take this magnitude, that's d. And that magnitude that is basically, you see here, when it's parallel to A, that's called the distance from the origin to the hyperplane. So when we talk about distance, it's always about a shortest distance, right? Not along any direction. You think about shortest distance, and that's usually what that is orthogonal to the hyperplane. How to make it orthogonal? Dot product. Okay? Now, in general, A is not normalized, so you can normalize it. Divide by norm of A. It will give you that. So this is the distance of the hyperplane itself from the origin. We will talk about distance of any point from, not the origin, the hyperplane. So we can divide, again, to reiterate, our n, I'm using still 2D images, but we can divide our n now to 2 half spaces. You can visualize it in your mind exactly like the 2D plane. You have a flat hyperplane. One side is, let's say, blue, the other side is red. Okay, do you have any questions so far? Now I'm going to switch to talking about the distance. You can ask more questions here. And after that, we're going to see how we can use this background that we learned here from algebra and a little geometric notion to formulate our classifier. I see no questions in chat. Okay, so for any point that does not lie on the hyperplane, what does it mean? If the point does not lie on our hyperplane, which is defined as all the point in Rn such that the inner product of A and x minus xc is 0, and A and xc are some vector in Rn. Now, by definition, if the point lies on the hyperplane, this inner product is 0. Any point that does not belong to the hyperplane, that means the inner product is not 0. Or in other words, if you expand it, A transpose times x is not equal to A transpose xc if x, right, does not lie on the hyperplane. So the constraint is violated. That defines the hyperplane. Now this gives us a way to define a distance from the hyperplane. There are many ways to talk about this distance. This is one of the easiest ones I could come up with. So we define the distance to be the amount that we deviate from this hyperplane using this equation that we have. Now, this amount that we deviate using this dot product is also orthogonal to the hyperplane because it is a projection using this dot product. So if there's any point such as x that is somewhere in the space, right, you have your hyperplane, you have the normal. I'm talking about a point here, x, right? It's just somewhere in the space. And you want to know This plane is too small for our example. Now, to know the distance, we need to talk about moving parallel to the plane normal, right? That's the direction that we get our distance is orthogonal, right, to the hyperplane. This is y of x. So, we take the dot product of an arbitrary point, right? Let's say this is xc was the translation, but is ultimately a point on the hyperplane, right? We take the distance of x with a point on the hyperplane, which is easy to pick xc because that was part of the definition. Take its dot product with a to get its magnitude in this orthogonal direction that I talked about, divided by the norm of a, because a possibly is not normalized. Then we get a function that is a signed distance. If you're the other side, right, because the normal vector is pointing to one particular direction, it will give you a negative of the same value. If it's completely mirrored, right, it will give you the negative of the same value. So this defines a signed distance using the hyperplane normal and an arbitrary point on the hyperplane. We picked xc again because we had it as part of the definition of our hyperplane. Now, what happens if you don't divide by the norm of a? Let's imagine what happens if a, let's say it has magnitude of 2. And we say, let's just not divide by norm of a. What do we get? The distance will be twice of what it should be, right? It's just going to scale the whole space. It makes your, let's say, Rn or R3 here to be, if you used to have 1 unit, right, that 1 unit becomes 2 units because the norm of A is 2. So it's going to scale it. The reason we normalize, because you don't want to scale the entire space. That doesn't make any sense. It changes the way we measure distance. So when we normalize, then it's only the direction, leave the space scale to be whatever it is, and only tells us the magnitude, this distance, right, along normal A. It is signed, it's very important, we will see now, because we care about which side we fall. So that's the basically, you've seen it maybe distance of point to line, point to plane. This is point to hyperplane, this is the same thing.
Can xc be just any arbitrary value on the hyperplane? Like, does it not matter what it is as long as it lies on the hyperplane?
Yeah, the reason it doesn't matter because you are projecting your vector along A, right? So that component of your vector is always the same. It is the other direction that maybe is bigger, but we don't care because the distance is measured along A, right? Which is great. It makes it super easy. Otherwise, it would be too complicated. Now, you might have seen formulas like D equals absolute value of AX plus BY plus, I don't know, C divided by square root of something like this, right? This is the same thing. This is a generalization of the distance, right, of a point to a hyperplane for any space. For 2D, of course, it's the distance of a point to a line. For 3D, it's the distance to the plane. So we use this inner product, dot product to generalize. Then we don't have to write down complicated equations like what I wrote. Again, there are many ways to derive this formula. This one seems to me to be the easiest way, because I can think about orthogonal projection, which is a section in chapter 13, but we're not heavily going over it in the lecture. You've seen it in Gram-Schmidt. Using the idea that the dot product allows us to project one vector along another vector, this formula is somewhat trivial. Okay, now let's talk about our problem, which is the maximum margin classifier. Why maximum margin? We'll see where it pops out in the formulation. So the topic, just to give you an overview, this is something you will come across in a machine learning course. Typically, machine learning is divided to supervised machine learning and unsupervised machine learning. Now that's the biggest categorization at this point we have. Anything that is not supervised is unsupervised. Then you have different categorization within unsupervised learning as well. So we are talking about supervised machine learning. Supervised machine learning itself can be categorized into two different problems. The first one is regression. You've seen regression before. We did linear regression, least squares regression, right? Anything that is related to finding a function that maps some inputs to outputs. That's the topic of regression, including the least squares regression that we discussed. In this case, the output values that are generally, in all cases, called target values or targets, these are real numbers. These are continuous. This is the topic of regression. When we talk about classification, then the targets are discrete categories, or you can call them labels. For example, that's circle and cross, right? Cats and dogs. Red car, blue car, black car, white car, yellow car. These are categories. It's not a real number. It's just a category that you could assign a number to them if you want to, but generally speaking, these are discrete and, in this case, mutually exclusive categories, right? A car that is yellow is not obviously blue. You can make it more complicated, and there are multi-labels. Maybe a car is blue and yellow at the same time, right? So we're talking about this simplest case, binary classification. It's a classification problem that we only deal with two mutually exclusive categories. Those circles and crosses that we had. So that's basically where we are. That's the problem we're dealing with. So our problem is that we want to find a classifier, and the classifier in this case is this line, or generally hyperplane, because whatever we talk about, it works for our N2. We start with 2D so we can understand and visualize it. So when I call it hyperplane here, it's really just a line, right? Just for emphasizing that this is true for n dimensions too. So we want to find a classifier, here a hyperplane, that can separate two different categories that we have here. In addition, we want to be able to use that model, the hyperplane, to classify a new input. If I give it a new example that it has never been seen before, I want the classifier to assign one of these two categories to that input, right? That's very important. That's usually historically, that's the distinguishing factor between statistics and machine learning, but the boundaries are very blurred. We usually want to build a model to make prediction later, not so much about the performance and the examples that we've seen already. The goal is that you have a good model, so when the new input comes, you can predict the output. That's the art, basically. But the precondition is that we perform well on the training data, that we will define it soon. We have two of these slides. Must be very important. It was not my mistake. Another technical term, if it's a new input, it's also called query or test input, right? So when you hear query or test input, it's just a new input that was not included in the given examples. Okay, so let's construct our problem. Usually when you try to build a model, you're given a data set. We have a data set that has pairs of input-output. Because it's supervised, so we know the input and we know the output. If it was unsupervised, if we don't talk about it, the outputs are also not given. You only have inputs. Which is why it's very difficult. It's a harder problem. So we have pairs of input-output. X, in this case, is a 2D vector, right? The location of these guys here. So the location of these points is the input. The output is the label, whether it's blue cross or red circle. Now, you can choose to show one of them. We can't work with blue circle and red cross. You need to pick numbers. You can choose +1, -1. That's very common, right? Now, it's totally up to you. Let's call red circle +1, right? So, or the other way around. It doesn't matter. So we have two categories. The outputs are +1, -1. Our model, we know that is a hyperplane. If it's a hyperplane, it will be of this form. I'm changing the notation a little because we had a x minus x c, right? And this was a transpose x minus a transpose xc. And I defined this previously d, but I'm calling it a0 here. I have my reasons to use a 0 or not here, but you could call it D, it doesn't matter. So I'm using different notation. So A0 is called the bias term. This is called the bias term in this model. Now, notice that we made an assumption that the model, right, that correctly classifies these two categories is a hyperplane. It's a line here, right? So you might ask, how do you know it's a line? We don't know, right? In reality, you wouldn't know. Probably it's not a line in real problems. Again, this is a toy example. I know it's a line, so I'm modeling this as a hyperplane. And this is historically one of the early methods for solving the classification problem. So what do I need to know here to get my line? What are we after? Now that we know a model structure, this hyperplane, I mean, there are infinite possibilities for this hyperplane, right? A itself is in R2. The bias term is just a real number, right? So I have 3 real numbers. I need to find some sort of suitable values for these 3 such that this model is good for solving my problem. So my problem is actually finding these parameters, just like the regression problem that we had. We were after the coefficients. Now, another insight is that, notice that if the bias is 0, right, this hyperplane goes through the origin. So if the bias is 0, you pick the model that has a 0 bias, right? You're only limited to models that will go through the origin. And as you can see here, the line that goes through the origin will underperform, right? Because the true solution is not going through the origin. So making the bias 0 will result in a model that has lower performance. So in fact, finding the correct value of the bias will give you the best performance, because that's the true location shifted subspace that we're looking for. So the low performance, if happens later in the next lecture, we'll see, when these labels are getting mixed, right? Then there's no specific line that separates them. That's so complicated. Whatever we talk about, it will break down. So when the problem becomes complicated, it's not so much about this bias. It's always good to have the correct value of it, right? Although that's a problem. But it's more about our hypothesis of the model, right? Probably this model is not so right in terms of parameters, or maybe if it's not a line, right? What if the data is separated like this? Clearly, this line cannot separate this, right? Which is a topic of Gaussian SVM that we will talk about. So it goes back mostly to this part, the model, the hypothesis, not so much about the bias term. Now, you will take a course in statistics and probability. Later in machine learning, they're bringing this notion of noise and randomness. Maybe at that point, you can pay attention when your teachers talk about the trade-off between bias and variance. It is good to find the perfect bias, right? But the more you try, it's a trade-off between the variance, this model part, error, and this constant term here, bias. So it's not that you can perfectly estimate it. So that was just insight on why it's important to have this term, the bias, right? Otherwise, we will be limited to all the lines that go through the origin in this case. All right, so we go ahead and formulate our problem, we do another trick. This is really for convenience, the change of notation. I'm going to stack all my parameters that I want to find into a vector and call it W, right? W is now in R3. That's what I do. And now, to keep it consistent with the dot product that I have, I'm going to append all my inputs with 1. And when I do that, then W transpose X is basically A transpose X plus A naught, right? This is really just a change of notation. It does not change anything about our data. But it's convenient because now I can talk about W transpose X bar being 0. Okay, with that change of notation, now I'm going to define hard margins. That's why it's called maximum margin or hard margin classifier. Define the line or hyperplane in general where this is not 0, right? That means it's shifted. So by now you know that A transpose A equals A transpose XC equals D, right? If the right-hand side, you have a real number, whatever it is, right? This is the shifted. This is the affine subspace. It's not going through the origin. But we define it relative to our hyperplane. Now, this hyperplane does not go through the origin because W was the stacked version with bias. Now, we have W transpose X bar equals 0. Now I have another line, which is W bar X, W transpose times X bar equals 1. And I have W bar X, W transpose X bar equals -1. I'm shifting them 1 unit. It was actually 1 divided by norm of W, but anyway. So this is basically defining a margin of 1, right, around my plane. So anything on and above this boundary, I'm going to call it class +1. Anything on and below this boundary, I'm going to call it class -1. This will give me 2. Now, this might seem odd. Next time, we're going to relax it a little bit, right? You might ask, why would you pick hard constraints, right? The reality data is going to blend in. And that will be a problem, but this is more a first version or more conceptual that makes sense to talk about. So this will give me 2 constraints. W transpose X bar I greater than or equal to 1 if the label is +1. W transpose X bar I less than or equal to -1 if the label is -1.
What happens if it's the data is like in between 1 and -1?
Well, it can, the question is what happens if data is between 1 and -1? It cannot be because it's a classification problem. All the labels that I have in data sets is 1, -1.
Couldn't there be, I get that, but couldn't there, like if you look at the actual data again, like wasn't there stuff closer? Or I guess maybe, are you just representing it differently right now? Because like when we looked at the other one where we had the X's and zeros, or and O's, like there was stuff closer to the classifier than just. I don't know, maybe.
No, you're right. Your question is that the points are going to be closer, right? Why are you setting this margin, right? What does it mean on and above? Because it falls between, right? Now, this distance is not 1, I reiterate. It's 1 over norm of W. What was the distance formula? I have to divide by the norm of W, right? It's not going to, otherwise it's going to scale the problem. So W is not normalized, something we search for it, right? So this distance, although I pick 1, right, it's variable because the choice of W can change it. So I leave it to the optimization to find what's the right choice. So 1 does not mean a hard. In fact, we're after this margin. That's the problem. Because I do not care if there is a point here, right? All that matters is all the points around these margins. The classifier will only try to fix this margin. In fact, these points do not have any weight in the optimization, which is the idea of the naming of support vector machine. These points become the support of finding the solution. So it's because of the distance, it's actually 1 over the norm of W. It's not 1. You could change 1, but it's not going to change anything because we can change W, right, during optimization. But later we will, next time we will talk about soft margin classifiers. We're going to relax it a little bit by adding extra variables. Now, if I combine these two constraints, you can do something smart. This one is really, the second one you can write it as negative of W transpose X bar I greater than or equal to 1, right? Then it sounds like if I multiply Y, which is just plus 1 or negative 1, right, by W transpose times X bar I can combine two inequalities into 1. So that's good. And that's true for all the points. And these are called inequality, right? A bigger than, greater than B. This means A greater than B or equal to B. Both are acceptable, right? All right, so now from here, you might have many ideas, but the simplest problem that you can formulate, right, is to, let's just minimize the norm of the weight, the vector. That's really the obvious idea, just like what we did in minimum norm solution of least squares. So this is the same as 1/2 norm W squared. So we say minimize 1/2 of norm squared of W, the vector of the parameters, subject to this constraint. Now this is new. We never talked about constrained optimization. This optimization is unusual in the sense that we're not just minimizing the norm of the W, we also need to respect the constraint. That means find a W that respects all the constraints and has the minimum norm, okay? This is an instance of quadratic programming. I'll talk about it later. Typically, when you see QPs, quadratic programs, these are nice problems. You have solvers and you can solve them, right? But this is arguably 50% or more of the problem. So a big part of the problem is to formulate your program, or problem. And we did it, right? So we came up with an idea, picked the model, formulated an optimization problem. It happens to be very famous. People know how to solve it. There are libraries for it, which is great. So that's half of the job. Formulate your problem. Next half is solving it. Again, the problem is constrained. It's different from what we had before. So I'm going to talk about a few concepts quickly, and then we go back to QPs. Training is the process of finding, or depending on the context, you might call it estimating or learning, the optimal value of W. Now, optimality is, again, with respect to the cost function, right? The objective you define. If you change it, then the notion of optimality will change. So training is the process of finding W. You could say that we are learning W or estimating it. Testing is the process of evaluating the trained model. Once you know the optimal W, then you use it to evaluate your model using some new examples that were not included in the training process. So you can talk about the performance of your model on the training set, right? Just the examples that you use to find W itself. Or sometimes people leave a portion of data out for validation. You didn't, let's say you left 10, 15% out not to be used for the training, and then you test on that. That's called a validation set. And then you might use completely new data that are not part of your training set, and that's called the test data, right? So good performance and training and validation data basically is necessary, but the challenge is having a good performance and test data. Okay, once you train your model and then you test it maybe on some examples, you want to deploy it. To deploy your model for new input, you want to make prediction. Now, suppose you have the W. What you can do, you can take the sign of W transpose X. Basically, you're calculating the sign distance, right? Scaling it by the norm of W will not change the sign of this. Calculate the sign distance, but only take the sign of it. That's your output for a new input. The sign function will give you -1 if X is less than 0, right? That's the definition of sign function in math. 0 if X is 0, and 1 if X is positive. Then what does it mean? If I give the classifier new input and it gives me -1, that means the new input belongs to that category that we assigned -1, right? So then we can make predictions. This is the prediction part. Now let's talk about QPs. Quadratic programs are a special type of optimization with constraints. The cost function has a special form. It's quadratic in the sense of vectorized version. So X transpose times Q times X plus Q times X. Small q is a row vector. So row vector times x column, you give a scalar. This part is also will give you a scalar. Q is assumed to be a symmetric matrix. That means Q transpose is the same as Q. So if you have an objective function of this form, plus some constraints, this is a quadratic program, but the constraints must be of this form. You can have equality constraints, right? This is just a linear system of equations. You can have the same linear system of equations, but it's an inequality constraint. So you have a matrix A times your vector X. X is your decision variable. That's what you solve for. This is called inequality constraint. This is lower bound, and this is upper bound. So you might say, I want to have an inequality constraint, right? Which is going to tell you it's a hyperplane. Those intersecting hyperplane will possibly help you to understand this. You have a bunch of them, and then there's a region that all of them agree with the constraint. The solution must be there. That's called a feasible solution. You might have equality constraint that must satisfy that equality. And we're allowed to have a lower bound and upper bound for the values of x. You might say my x should be bigger than, let's say, 0, less than 10, bigger than -5, something like that. Now, if there is a non-empty set, this is why quadratic programs are nice. This is a subset of convex optimization. If there is a set, such as C, that is not empty, that means considering all the constraints, there is a region in the space that we can search for something, right? There's at least one point there. Then the solution exists and it's unique. We can solve it and find the solution uniquely. So that makes quadratic programs very nice. Whenever you have a problem that is formulated as a QP, you can solve using a QP solver, and if the solution exists, that means the set that's considering all the constraints is non-empty, then it will be unique. Now, you might have seen in minimum norm problem just the equality constraint, right? In the minimum norm, you had just the equality constraint. Here we see inequality constraints. So especially in control, this is very important because they use QP solvers extensively. A lot of controllers and the robots you see, they use QP solvers. For example, you have bounds on your actuator torques, right? You're not going to have infinite torque to move the robot the way you want. That's just not possible. Or the range of motion for a manipulator or the leg of a robot, right? It has a limited range. You cannot just move it the way you want. Or, for example, a car that is moving, it cannot move to the lateral direction, right? It has some constraints on the motion. The lateral velocity is not something that you can control in the sense that you can just move immediately to that direction. So all these constraints become very important when you want to control a vehicle or robot. And that's why QPs are great for these problems. Which is basically a simple version of that is what you do in project 3. A more advanced version of that is what we do in the lab on the robot. Okay, so Q must be positive definite too. And the definition of positive definiteness is that all the eigenvalues are positive. That's the easy definition. Or for any x that is non-zero, this quadratic term is positive. Then Q is positive definite. Okay, now let's go to the code. So next time we're going to talk about soft margin classifier and Gaussian support vector machine, which is an extension of what we talked about today. Now, the first notebook that I prepared for you, it is just to practice with QP. There's a really nice QP solver in Julia. It's called Operator Splitting Quadratic Programming, OSQP. So I'm including this. I need to. So this line here is the same thing as adding the package. It's just a different way of doing it. So I'm adding OSQP package. You will need another package to work with compact and sparse matrices. This is my quadratic program. Now, to have a quadratic program, right, it needs to be 1/2. 1/2 is for the beauty, but let's say it's 1. You can manipulate it to be this form, that you have 1/2 x transpose some matrix, Q, times x plus some row matrix, right, small q times x. In this example that we have, it's basically 2D example. Q is 2 by 2. You see that? 4, 1, 1, 2. And my row vector is 1 and 1. Now, I only have inequality constraints here, right? Now, notice that this is a compact way of writing inequality because it's bigger and that's smaller, right? So this is actually 2 set of constraints. Depending on the language and the library, they might ask you to enter your constraints in different ways, right? That's just, you're going to check the documentation and see how it's done. The way this package works is like this. It wants you to first create that Q, we call it P here. And it must be of this type of a sparse matrix. That's why I'm loading this compact sparse arrays. That's a requirement for the OSQP package. So define your Q or P matrix. Q, as we talked. Then combine all the constraints into this form, that it's a matrix A times your vector x, some lower bound, some upper bound. You can always do that. That's just a different way of writing our equations. Now, what if we have x greater than 0? There's no upper bound, right? You set the upper bound to be infinity. The solver will understand. So we combine all the constraints already done here. So we need to define A, lower bound L, and U. Then we create an object of OSQP model. I'm calling it my problem. To set up the problem, we use this API, application programming interface. This is just a method that is provided to us to set up our problem. So I pass the object, semicolon, then define P, Q, A, L, and U. Then solve it. Okay, that's all you need to do to solve a QP. It is not necessary to know what's going on inside, right? It is great if you're interested. You would like to learn how to build a solver. But if you only care about solving your problem, that's perfectly fine. You can use the solver. So you see some information about the package. And I didn't explicitly print the result. It will give you the result here. There's a bunch of outputs. This first part is your result. And other examples, I'm explicitly calling the results. We see the vector. So the solution to the problem is just this vector, 2D vector. Another QP. So we just have, so it's always the same structure, right? You will have different matrices and bounds. So we only need to change P, Q, A, L, and U. We do that exactly the same way. We solve the problem. We find the solution again. It took 25 iterations, right? It's the runtime is almost nothing, so it's really fast. The solver can find a solution very fast. So please take a look at this file. This is just for practicing QP. You can create other examples and test the solver. Let's go back to our classifier. I load the OSQP package and compat again. You might see different text. This is because I didn't run it since last year. It's just updating some packages. Once a year, I run this code. This is the second time. So what was our problem? Our problem was minimize norm of W squared, norm of W squared, which is 1/2 W transpose times W, right? And the constraint was yi times W transpose times xi, greater than or equal to 0, to 1. So that's our problem. Now, I'm creating a data set myself. You can try to find a data set and load it, something more realistic, but this is a simple data set I'm generating by just looping and some numbers. I'm generating somewhat balanced data set that I have fairly equal inputs in each category, right? Because if your data set is imbalanced, that's usually, it can be sometimes a problem in some domains. Okay, we can so because it's 2D, I can also visualize and see the output. This is the data set I generated. Now, you play with it, change the numbers, you will get different data points. See if you can break it, because if you mix up these points, this classifier will break down. That's what I'm going to do next time. That's why it's going to be soft margin. So we don't want it to get too irritated if now suddenly one blue dot is moving to the other side, right? So we accept some level of, we can show some tolerance and accept some error. And still, it's going to be a good model. Okay, so this is the visualization, and I played this as well. I'm defining my problem. Now, you need to look into these constraints, see how I converted that program into these matrices, because that's not how I wrote it, right? P is easy because we have W transpose times W. Basically, it's the identity matrix, right? In our quadratic program. Q is 0 because we only have, let me write it here. So we have 1/2 W transpose W, right? And our QP has this form of one-half X transpose QX plus Q. I think it was just QX. Now, obviously, Q is 0. I don't have it, and this is the identity matrix in my problem here. So these two are easy. The hard part is the constraint. The constraint is basically here. So you see that one of the bounds I set to negative of infinity, because my constraint is telling me to be greater than or equal to 1, right? To tell solver that one side is open, we use infinity. Now, there's some negative sign going on here. You should go through it, make sense of it. It's great to follow up on Piazza or office hours. But anyway, I converted that program and constraints to this form. So I pass my lower bound, upper bound, A and Q and P. And just like the toy example we had, this will solve the problem for you. Now, once you solve the problem, you can allocate your output to the result, for example, and then results.x will give you the output. So I print the result.x here, and this line is basically, if you remember, this will be W, which is A, and A naught, right? Okay, so it is a 3D vector. So that is the optimal value for the W. You can visualize it to see the output. This is the trained model, okay? You can change the data set again, play with it. You should be able to get a different model and see if you can break it. You should be able to break it down if red and blue gets blended. So this is it for today. Next time we will talk about soft margin and Gaussian SVM. When it's nonlinear, what can we do? Line is not obviously always a great model. See you on Wednesday.